Well, thanks everybody. Welcome to the third and final tutorial. Today we're going to be talking about model comparisons and robustness. So a general kind of framework for computational modeling, you want to first generate some hypotheses and build models. So a general framework for doing computational modeling, we want to generate some hypotheses, and then we build models for each of these hypotheses and fit the models to the data. So far we covered the first three steps, but now we're going to focus here on how to determine which is the best models and to develop some interpretation of these results. Now, this talk is kind of in two main parts. We're first going to talk about model comparisons, and then we're going to talk about how we can test for the robustness of these comparisons of our model to make sure that we're able to interpret them fair. And there's this oft-quoted a statement by George Box that essentially all models are wrong, but some are useful. Now, what does that mean? Well, what we want to do with a model is we want the model to be as simple as possible, but not simpler, right? And a good explanation for this comes from Jorge Luis Borges, who has this really nice a metaphor in the short story called On Exactitude in Science. And he talks about an empire that built where the art of cartography attained such perfection that the Cartographers Guild created a map of the empire, which is exactly the sides of the empire that coincided point for point with it. And this is not what we want to do with modeling. We don't want to capture the phenomena one-to-one because such a model is completely useless. Such a map that captures every single detail is useless because we might as well use the environment instead. Rather, we want to capture the broad strokes. We want to capture the main mechanisms in a compressed format that allows us to interpret something. So this is why we want our models to be as simple as possible, but not simpler, because if we're missing important mechanisms, key details from behavior that our model can capture, then it's not going to be useful either. So, right, so we got to strike this fine balance. And one illustration for how this balance plays out in real data is this example here from trying to predict London's daily temperature in the year 2000. Right, so this is probably going to be quite different now, 20 years later, unfortunately. But what we can try to do here is model the temperature as a function of the day of the year, right? And we can try this with many different types of models. And here in the dashed black line, we have a relatively simple model, a third-degree polynomial. And then in the solid line here, we have a much higher degree, a 12-degree polynomial, right? So they look quite similar. Maybe the 12-degree polynomial has a couple more wiggles. But it's really when we're looking at the difference between fitting and prediction, where the differences between these models play out. And so here I'm going to show you actually many different types of models across many different degrees of polynomial. So the more degrees of polynomial, the more complexity in the model, the more flexibility in capturing more diverse patterns. And so the error in terms of fitting, this line here, continues to decrease as we increase complexity in the model. But not so for predicting. When we hold out some data and try to predict unobserved data, we initially see the model performing better as we add more degrees, right, in terms of predicting. But then it peters out, and then actually in the upper end of complexity, we start getting more and more prediction error. We start to capture noise in the data that's not inherent in it, that's not essential to it, and our model has overfit. So this is one of the key ideas behind capturing the goodness of the fit of a model. We want to kind of find the balance in this tug of war between being as simple as possible, but yet still capturing the patterns of the data. In this talk today, we'll talk about two different theoretical approaches to capturing goodness, to do goodness of fit. One is based on maximum likelihood, which is one of the simpler approaches. And this is capturing a single point estimate of a single set of parameters in the space of possible parameters that captures the data the best. And we're going to contrast this with Bayesian model selection, which looks at the relative evidence for one model versus another. Now, these are the main theoretical approaches. But in practice, we can actually think about two, based on these rows, where a most common and simple approach for doing model estimation, model comparison, is based on AIC or BIC. And these measures, even though they belong to different camps, are actually quite similar in practice. Rather than take something like a maximum likelihood approach, where BIC has a Bayesian interpretation. Now, more complex is using prediction error directly through cross-validation, or essentially relying on Bayesian Occam's razor, where Bayesian principles allow us to naturally find this right fit, where Bayes' rule is essentially allows us to have a preference for simplicity baked in to our model estimation. And I'm going to describe methods using Markov chain Monte Carlo. In theory, we can separate based on these two different columns, but in practice, it's probably more appropriate to kind of select either penalizing for the number of parameters or doing this prediction error / Bayesian approach in the bottom row. So we'll start first with just explaining the overall theoretical difference between maximum likelihood estimation and Bayesian model selection. So maximum likelihood estimation, as we showed earlier in tutorial 2, the goal is to quantify the goodness of fit for a single set of parameter values, theta hat, that provides the best fit to the data. So we're trying to find an argmax of theta hat, some value of theta hat that maximizes the likelihood. And now I've augmented this notation a little bit to also include M to specify a specific model, because now we're having multiple models in the mix. Okay. And the approach to avoid overfitting is to add a penalty for the number of parameters. And this is used by AIC, but also approaches like BIC as well. We can penalize the number of parameters, or we can use cross-validation to kind of separate into test set and prediction sets, like we saw with the London temperature data, and to try to use cross-validation to test directly for predictive power. And maximum likelihood estimation only considers goodness of fit at a single point in the whole parameter space of the model. Okay. Now, in Bayesian model selection, the goal is to capture how well a given model captures the data using the marginal likelihood, which is across all possible parameter values of that model. Okay, so the likelihood here is called the marginal likelihood. We've integrated out the parameters. So we've removed the parameters from the conditional here, and this requires computing this integral across all possible parameter values of the model. And then we're computing the likelihood of the model at all possible parameter values. Now, this integration is very computationally costly, which is why most approaches only approximate this value using BIC based on some assumptions or MCMC sampling. But this approach also naturally penalizes for complexity, right? We're not only measuring the model at its best, we're measuring models across the whole space of fits. We're capturing likelihood across all possible parameter values. So if the model has extra flexibility, it's going to be also be quite bad at some in some regions of that flexibility, right? In some regions of that parameter space, and we're going to penalize the model for that because we're essentially computing the likelihood at all regions of the parameter space, right? So we don't only test the model at its best, but we also test it at its worst. So in this way, we're able to naturally penalize for complexity. This is known as Bayesian's Occam razor. Now, as I mentioned, in theory, these are the main conceptual differences, but in practice, some of these approaches are quite similar. And actually, computing AIC and BAC are very similar in practice. We'll start with this approach because it's definitely the simplest. So here's the definition for AIC, Akaike's information criterion. And we can break it up into two main components. So AIC, if you might recognize this term here from earlier this morning, this is capturing the fit, and this is -2 times the log likelihood. Right? So this is known as the deviance, as I mentioned earlier, which is just 2 times the negative log likelihood, right? The higher that value is, the worse the fit, the higher the loss, okay? So essentially what we can do before maximum likelihood estimation to get theta, we find the best theta, and then we compute 2 times the negative log likelihood at given that set of parameters. So this is capturing how well the model fits the data. You also want to penalize for complexity. And we do this by adding an additional loss term that is 2 times the number of parameters in the model, K. K is just the number of parameters. So does anyone remember how many parameters our Q-learning model has from earlier? 2, right? So essentially we would take the 2 times negative log likelihood of the fits with the maximum likelihood estimate plus 2 times 2. And that we actually, we add an extra penalty of 4 to that negative log likelihood based on those parameters. Value shaping has 1 more parameter. Decision biasing has 2 more parameters. We add those penalty terms based on the number of parameters. Now, I'll start with trying to really briefly explain the theory behind what AIC is trying to capture. It comes from information theory. It's trying to capture the relative information lost by a given model that's trying to capture some objective reality. So map here, these described objective realities are of X. It's this point here in some space. And each of these models is trying to capture it. The model has a range of possible parameter values. that gives us some flexibility. The maximum likelihood is the closest point in that space. And so this is this kind of high-level theory. I don't expect you to really fully understand this math here, but in more practically, AIC should be thought of as trying to approximate cross-validation. So asymptotically, in the limit of infinite data, and for linear regression and linear mixed effects regression, AIC is equivalent to what's called leave one out cross-validation. So essentially, each of these blocks represents one point of data, so one choice from a model. And what we're doing is we're iterating over this data set, training the model on all the data except for one data point, leaving that out as a test point, and then predicting the model on that out of sample on that test point. And we iterate, changing which data point we leave out. And so then we kind of run through the whole data set and predict in this way using cross-validation. So in the limited infinite data and for linear regression models, AIC is equivalent to this leave one out prediction error. Yet in practice, it's often used for models that are not linear regression models, and certainly always short of infinite data. And so more generally, we can think about AIC as being one of the more lax goodness of fit measures we introduce in this tutorial, and it's more prone to overfitting, to prefer an overfit model than some of the other measures, okay? So high level theory in practice is really quite trying to describe cross-validation error in this limiting context. BIC is actually very similar in practice to AIC. We have exactly the same fit term here. Again, we achieve this via maximum likelihood estimation. But then we add a different complexity term here. So it's K, the number of parameters again, but rather than just times 2, we take log n, which is where n is the number of data points that we have in the data, right? So when n, the number of data points is 8 or more, then this term here is going to be larger than for AIC. So BIC in practice penalizes much more strongly for the number of parameters in the model. So it's going to be more likely to choose simpler models than AIC does, as long as you have 8 data points or more when you're estimating it. I'm going to go through the theory first because the BIC, as it says in its name, has a Bayesian interpretation. Bayesian model selection sometimes relies on what's known as Bayes factors to quantify the evidence for one model over another. Okay, so sometimes it's written like this: BF for Bayes factor, and sometimes subscripted 1, 2 to indicate the evidence for model 1 over model 2. Maybe Bayes factors are being used less and less these days to do the model comparisons, but we can talk about that later. But in general, we can think of a Bayes factor of 1 means that ratio is equivalent. So there's no evidence for either model, exactly even evidence. When Bayes factor is much larger than 1, this model 1 is much more likely than model 2. So we have strong evidence for model 1 when that value is very large. When that value is much smaller than 1, we have evidence for model 2 instead of model 1. Okay. And so what the BIC does is it tries to approximate this likelihood using the maximum likelihood estimate and making some assumptions. So how does it do this? As I mentioned previously, to compute this term here, the marginal likelihood requires integrating over all possible parameter values. And this is intractable for most interesting problems. What the BIC does is it tries to approximate this term here, which is -2 times this term. And it does so, and by doing so, it allows us to compute a Bayes factor, where we can essentially take an exponent of the difference between the two BICs in this format. So this is the theory behind Bayes factors, but this interpretation is not without controversy. And the Lewandowski and Farrell book has a nice discussion about this, because the assumptions are hardly ever met or even unpacked, right? So essentially, BIC is making some assumptions about the shape of the prior on parameters, and it's accomplishing this approximation of the marginal likelihood based on these assumptions. But this is often not really unpacked, and it can be controversial. So, but in practice, what we can think about BICs is just more of a generally stricter approach to penalize for complexity compared to AIC, and less likely to prefer an overfit model, right? Since log of n is greater than 2 when there are at least 8 data points. And note again that we're using natural log here, not base 10 log. This is the common convention. So in the code notebook, we have some code for maximum likely estimation and compute BIC and AIC. So what we first did is we simulated some data from a Q-learning agent, but we put it in a social learning situation, okay? So these dots on the bottom represent the choices that the agent made with this Q-learning agent. And above, we also represent 3 other agents learning in the same environment. And these are the socially observable choices that the agent has access to. This Q-learning agent doesn't make use of this information, but we don't know that. We also want to consider social learning models as well. This black line represents the rewards that they got for each of these choices. So what we're giving the model is this information here. We're giving the models information about the choices the agent made, the rewards that they got, but also the social information that could inform their choices. We don't know, and we want to see how that information affected their choices, if at all. And what I've done here is I fit a Q-learning model and a value shaping model to each of the 4 agents, right? So not only this agent, but each of these other agents as well. And in this, for the simulation, for simplicity, we used a Q-learning model, although we also test the value shaping model as well. And here I plotted the AIC and BIC values for each of these simulated agents. So each pair of dots is a simulated agent, and the lines are connecting them together, where the goodness of fit is showing the AIC for the left column and BIC for the right column. So what we can see, there's a lot of variability overall, but in general, what we see for the AIC model is that we actually don't see that much distinction between Q-learning and value shaping, right? Essentially, lower is better. Some of them are quite similar. But BIC, which penalizes much more strongly for the extra parameter that value shaping has, is more likely to correctly identify that the Q-learning model is a true underlying model for these agents. So this is a situation where AIC is maybe not penalizing enough for complexity, and BIC seems to be doing a better job and identifies a true model. Although this is a very small data set here, but you have access to the code in the tutorial notebook where you can take a look at how these simulations are done and very easily scale up to other settings. There are several different variants of cross-validation as well. So I showed you on a couple slides ago, leave one round out cross-validation, which can use the natural distinction between independent rounds or blocks in experiment to separate the data. Sometimes your data, though, has no natural structure like this, and you'll have to kind of break it up into k equally sized slices using k-fold cross-validation, right? So we have this continuous data set. We kind of arbitrarily decide we're going to break it up to k different folds, and then we iterate this way. Or we might also have leave one out cross-validation, which is the extreme case where we iteratively leave out a single data point at a time on the training set. Now, you'll note that for every slice or for every data fold, for every data point we have to estimate the model anew, right, by computing the maximum likely estimate. And this takes a long time. So you have to also be wary that doing cross-validation is much more costly. It's going to be k times as costly, or the number of rounds times as costly as just doing maximum likelihood on the overall data set. But it's going to be more robust, and you'll get a better estimate about fit. And you'll also get multiple estimates about the parameters. You won't get a single maximum likely estimate, but multiple estimates. And this will give you an idea about the variability about the parameters, but also give you perhaps more robust estimates when you compute a mean or a median over all these rounds. So every single one of these slices gives you different estimates. We pull them together, we're probably going to get a better estimate overall. Okay, good. Now, this is the part where we get Bayesian, and we can try to get a bit distributional here. There's 3 main reasons why we want to be Bayesian about modeling. First of all, what we get from it is not just a point estimate, but we get an entire probability distribution of our functions, right? So remember that with maximum likely estimate, we're getting a single point in the parameter space, but sometimes it looks like this, right? It's much multimodal. We want to get a sense of all the parameters that seem like the end of the data. Second, rather than assuming participants are independent samples, we can model hierarchical relationships right? And this is also sometimes nice within subject designs. So this is a plot from a recent paper of mine. We modeled how time pressure influences exploration and learning in a bandit task, where time pressure manipulations was within subjects. The same subject did this task with time pressure and without time pressure. And what we can model is how that changes people's parameter values. So we have kind of this value directness parameter and their uncertainty bonus parameter. And we can model how this changes within each individual. Now, individuals have a lot of variability, but we can show that within each individual, we have these reliable changes in these parameters, okay? We might also want to get a sense of what the group looks like. So Walter made this very nice figure here. We can imagine the learning rates for 3 different individuals. Maybe 2 people are very studious, they're learning very, very intensely, and 1 person is chill, taking a bit of a break, watching some TV shows, eating ramen, and their learning rate is very low. But what we'll get from that is the overall distribution of alpha across the group as well, okay? And lastly, we also want to use Bayesian model estimation, because we can naturally avoid overfitting. And this is through Bayesian's Occam razor, which I talked about earlier. Since we evaluate the model across the entire range of parameters, we also essentially penalize for more complex models, because some of those more complex models are just going to have parameter values that are not very realistic. So these are the reasons why we want to do Bayesian model estimation. Okay, time to do a little bit of math. So we want to compute a posterior distribution over parameters. Previously, we had used maximum likelihood estimation to provide a single point estimate, right? This is the theta hat we found before. But now we want the full distribution of parameters suggested by the data in our choice of model. And this is this term here, right? We want to get a posterior probability about the parameters given the data in a specific model. And with Bayes' rule, this is proportional to the prior, so the prior probability of parameters and models, and the likelihood, right? For a specific for a specific model and for a specific parameter, it's the probability of the data, right? So again, this is quite simple. Our likelihood function already does this. When we give it a set of parameters, we give it a parameter, it gives us a likelihood. But this is very complicated because integrating over all possible parameter values means we had to run this for every single combination. When parameters are continuous values, that's an infinite space. We just can't do this analytically, okay? So this is the kind of problem that we have. We want to compute a posterior distribution, but we can't integrate over all possible parameters. So this is where Markov chain Monte Carlo comes in, and it's operating on 2 very simple concepts that we connect together. So the problem is we want to model a probability distribution that is difficult to compute analytically. And the solution is to acquire random samples that approximate this distribution. Okay, and it does so using 2 ideas. Markov chain is the first part of the model of MCMC. The first MC in MCMC is Markov chains are sequential processes where each random sample is used as a stepping stone to generate the next sample. There's a special property of Markov chains, or the Markov chains that we use in MCMC sampling, is that it has as its equilibrium distribution the target distribution we're trying to approximate. So in its equilibrium, this Markov chain is going to look like a posterior distribution that we want to approximate. It takes some samples to get there, but assuming you have enough samples, it's going to look like the target distribution we're trying to estimate. Sorry. Now the second concept is even simpler. It's a Monte Carlo concept, and this is named after a casino, I think, in Monaco. And it's a basic idea in statistics that with the law of large numbers, enough randomly drawn samples will approximate the distribution. You flip a coin enough times, the outcomes will represent the true outcome. Okay, so we combine these 2 things together. And here I'm showing you some pseudocode for describing the simplest possible flavor of MCMC. And this is known as Metropolis Hastings. So Metropolis Hastings is a very simple rejection sampler. And so I'll walk you through how all this works. So we first start off with some sort of prior distribution over parameters. And we can imagine one very simple one is just based on a uniform distribution, right? So here's some lower bound, here's an upper bound on parameters. And imagine theta can be anywhere in that space. So what we do is we first sample an initial point, theta 0, from this space. And let's imagine this gray circle is this. Okay. What we then do is we compute the likelihood of data given these parameters, right? We have a likelihood function already. We plug in this parameter into the likelihood function. We estimate the likelihood. Good. Now, the first step we already have. We always instruct the first sample. And so for every other sample, we're going to have a sample from some transition distribution. Okay, so this is it's a condition on the previous sample, and it's a probability of the new sample. And so one very simple approach to do this is to add some noise to the previous sample. We can add some Gaussian noise, but there's other possible transition distributions as well. So imagine we add some noise to this distribution, we get this new sample here. We compute the likelihood, and now we have to decide: do we accept this new sample, or do we rather try again and sample, try to get a better sample? Okay. Now we accept this new sample with a probability that's proportional to how much of an improvement it is over the previous one. Right? We compute the likelihood of this initial sample. We compute the likelihood of this new sample. If this new sample has a better likelihood, right, lower negative log likelihood, lower log loss, then it's a better fit, then we're more likely to accept it. We still sometimes accept it if it's worse, but we're more likely to accept it if it's better. Okay, and so an example of a sample that was rejected is this unfilled dot, where the model took another sample instead and then accepted this one instead. Okay, so this process is repeated for a long sequence of samples, sometimes several thousand is quite common, like 2,000, 3,000, 4,000. And then what you have at the end is a series of these gray filled in dots, right? We've rejected the ones that are not filled in, and we can build something like a histogram of these dots that we've sampled, and that represents the posterior distribution of our parameters. And that's it, right? So then this estimate that we get is the posterior distribution of what parameters the data suggests. Okay. Any questions at this point? Okay, and so here's an animation of this process in motion, right? So I'll probably play this again just so people can catch it. I think the red dots represent rejected samples, whereas the green ones are accepted. And what I think you see at the very front is that the transition distribution is a Gaussian, right? Centered on the previous sample. We just add some Gaussian noise essentially to jitter it around. And on the left here, we have the density plot of the parameter that we're estimating. Okay. Now, what does this actually look like in practice? There's a variety of different MCMC samplers that kind of take care of all the stuff like Stephanie is asking about. How do we actually do this? You don't have to worry about it. Stan is probably the most common approach, and you can use R as interface to interface with it. But Stan kind of has his own language for how we define models. Models are defined in terms of essentially relating a set of variables together. So here's like a Bayesian plate location illustration of how variables are related together, where, for instance, an alpha parameter might be related based on some population mean on alpha. That's a population standard deviation on alpha. And essentially relate them together based on assumptions about distributional shapes, right? So you might assume things are a Gaussian distribution or assume things are an exponential distribution. So everything works in terms of distributions, in terms of relating variables to one another, in terms of the structure of the model. That's how you build models in Stan. Now, there's also methods in Python. PyMC is also another common approach, and uses also a very similar approach. You're defining distributions for the different parameter priors that you have, and you're relating them to one another in kind of this mathematical format. In the code notebook, we have a tutorial. Maybe I'll show this very quickly. So we've coded up for your viewing pleasure, the Q-learning model in Stan. It's also quite trivial to turn this into a value shaping model or decision biasing model, as we've shown previously. So this is what it looks like. You can feel free to use this code for your own work later. Now here's how we run the model estimation. We kind of compile some simulated data, specify some parameters in the model, number of chains right? So we're running multiple chains to make sure that we have good results, not only a single chain of the sampler. We specify the warm-up, the part we throw away before we get going, and the number of actual samples that we get. I set it to very small values here because I'm running this in a code notebook. People typically use much more than this. I prepare the data into a list to feed into Stan, and here we run it. This probably takes about a minute to run. Now let's look at the results. So what I'm showing you here are the posterior estimates for the alpha parameter, the beta parameter for Q-learning agents, and the dashed vertical line shows you what the true underlying parameter values were, which corresponds really well to what the kind of the mode of these posterior estimates. Right? So the posterior estimation, the Bayesian estimation seems to have done a good job, despite the fact that we use relatively little data and relatively few samples to estimate this. In terms of actually doing model comparison with Bayesian methods, these methods can get quite complex quite quickly, and it can seem quite daunting with a variety of kind of alphabet soup of these different terms like parietal smooth importance sampling, PSIS, or LUIC, which is leave one out cross-validation information criteria, or WAIC, which is widely applicable information criteria. And so in general, we don't want to have time to get into the details. So these special terms are just a way to kind of adapt this notion of out-of-sample predictions for distributions of parameters instead of a single set of parameters. And so the basic principle is like something like LUIC, for instance. So this is the output when we're trying to do model comparison from that Q-learning model I just showed you. A very simple term you might recognize how to interpret is LUIC, very similar to AIC or BIC. And this term here tells you how good of a fit it is, right? And I feel like you have an estimate of is higher better or lower better? Right, so lower is better, and so this is maybe already giving some intuitions about how to interpret this using very similar concepts from AIC and BIC, which are other information criteria. But for more details, I would suggest refer you to this paper by Aki Ventari or this fantastic textbook by Richard McElrath, Statistical Rethinking, where he goes into much more details about this in a very intuitive way. But in the scope of this tutorial, we won't have enough time. I don't want to keep you guys here all day and also tomorrow, just to go into details with these Bayesian model comparisons. But in general, I want to make sure that there's no confusions, and now would be a good time for some questions before we wrap up. So I'll quickly do a summary of part one, and then we'll take some questions, okay? So I've described the maximum likelihood in the Bayesian model selection approaches to doing model estimation, different theoretical frameworks, but in practice, it seems that it's more helpful to kind of delineate based on these different rows of this table, which is which is to penalize for parameters or explicitly test prediction error through cross-validation or with MCMC sampling. Let's continue on to part two, robustness. I'm going to talk about 3 robustness checks. I think this is exactly the answer to Stephanie's question earlier about how do I know if I need to go to more complex Bayesian approaches. And these different approaches essentially allow us to test different aspects about our modeling framework, our task design, right? So this can also inform us how we might want to modify our experiments even before we've collected any data and gone through all that effort, right? And maybe even suggest we should revise our hypotheses or revise our models that we want to test due to some issues with how well we can interpret the results. The first approach I'll talk about is model recovery, which is trying to capture whether or not the data can actually differentiate the models we are considering. Could there be model mimicry where just one model always wins, even if it's not the true model? And so this is what we're trying to uncover with that. The second robustness check is parameter recovery. Are the parameters of our model actually capturing distinct phenomena? Sometimes we want to test hypotheses where we have these parameters capturing these different interesting hypotheses, but the data simply isn't strong enough to distinguish between them, or these different phenomena are not necessarily independent or uniquely identifiable, such that sometimes there could be issues where one parameter is correlated with the other one, such that you can change one parameter to also capture behavior with the other one as well, right? So a parameter recovery is a way to test if we can really get reliable parameter estimates that are meaningfully unique and avoid issues of misspecification. And then lastly, we also want the model to generate realistic participant behavior as well. not only capturing the irrelevant aspects about behavior, but also the relevant ones for performance, right? To produce the same behavioral patterns and that we saw in the data. And so this is the third check we'll talk about. Good. So with model recovery, this is the general pipeline, and we can do this even before we have any data by using kind of an a priori best guess about parameters that we might expect in the population, or we can do this after we collect the data using our participant estimates about a set of parameters. Okay, so using these parameters, either a priori or based on participant data, we can simulate data from our models. Okay, parameterized with a set of parameters. Give it to a model, we then simulate data. Then what we can do is we can use the same suite of models that we'll be testing to then estimate that simulated data. And then we'll produce some, each of these models will have a fitness and fit, and we'll also have a set of parameters for them that corresponds to either their maximum likelihood or their posterior distribution, okay? Now, the main goal here is to figure out how often does the correct model that actually simulated data also produce the best fit. So there's two main analyses that we want to look at here. One is called the inversion matrix. One is called the one is called the confusion matrix. One is the inversion matrix. I'll start with this because it's simpler. Okay. So essentially, on the rows here are each of the different simulating models. Okay. So here, model 1 simulated all the data. Model 2 simulated this data. Model 3, 4, 5. And on the columns here is the proportion of times that a specific model provided the best fit for the data. Okay, had the best fit. You can do any method you want. This is essentially testing the robustness of your modeling framework, right? So if you're using BIC, you can use BIC here. If you're using Bayesian approaches, you should use Bayesian approaches here. Okay. So what this tells us is that, okay, for model 1 simulated data, model 1 always fits best. Great. For model 2 simulated data, we also get model 2 fitting best, but sometimes model 1 wins out very infrequently. Model 3 runs into some issues here. It only correctly identifies 54% of the time, because actually more often model 1 is actually better than it, even though it did not generate the data. Similar story for model 4, and model 5 is a bit of a mess. It seems that model 1, 3, and 4 are also quite correctly. So what this tells us, a couple of things, is that models 3 and 4 have some issues with recoverability, right? But it also seems that there's some issues here with model 1 as well. So this is why we want to then compute the inversion matrix, which essentially inverts this term here using Bayes' rule. We have the formula in the code notebook. I won't go into too much details here, but here now the columns will sum to 1. If we find that a specific model was the best fit model in the data, what's the probability it also was the true generating model? Okay, this is telling a very different quantity, because when we run our actual model comparisons, we only ever see this value, but which is the best model. What we don't know is what model actually generated the data for our participants. We don't have access to that. But what this tells us is that how confident can we be that when a certain model was correct, it actually truly was the best generating model. And I think the most notable thing here is that for model 1, right, we're actually not very confident that when model 1 wins, it was the best generating model in the environment. And the reason for that is clear when we look down this column here. Look at model 3, look at model 4, right? When model 1 wins, there's also a reasonable probability that model 3 or model 4 actually generated the data, right? If we switch over here, recall that when model 3 or model 4 generated the data, model 1 was the best fit a third of the time, okay? So what this plot here is telling us is that if model 1 wins, we still can't be certain that model 1 actually was a true model, because it also mimics these ones, right? And so this is telling us a very different picture than this first plot. This is an easier plot to produce, but I think this other plot here on the right is much more informative. That's what we really want to be careful about, because all we ever see in our actual data is which model wins. And what does it mean when it wins? Well, this is what that plot on the right is telling us. Sometimes when it wins, you still can't be certain that it truly was the best model. So when you have a situation like this, you should rethink your modeling framework. You might need to rethink your task, right? Your task might not have enough data for you to differentiate between these models. You might also want to design this, rethink the stimuli or the probabilities behind the different outcomes so we can better distinguish between models, especially 3, 4, and 1. You might want to change the modeling framework. Maybe you're not penalizing strongly enough for the more complex models. Maybe model 1 is very complex and it's overfitting data from model 3 and 4 because you're not penalizing enough for complexity. You might also want to adopt something like cross-validation or other Bayesian approaches to get a better estimate. Okay, but or you might want to revise the hypotheses you want to consider. Maybe it just is not feasible, no matter how much you adapt the task and change the modeling framework to distinguish between models 1, 3, and 4. I often try to run this for the same amounts of data as I have from participants to essentially get the same representative sample. But it's a bit hard to say, right? Sometimes recoverability for some models may be 70%, and that's as good as we can get because we've estimated this on children, and children are a little bit noisy anyways, right? But sometimes we have, I think Stefano was showing you had 100% recoverability for every single model, right? And I'm not exactly sure what the details about how you did it that way, but I feel that's also a really high bar to reach, right? You might not always get to Stefano level recoverability in all contexts, but that's fine, perhaps, right? So I feel like ultimately it's what you can justify to yourself and to the reviewers as a scientist, right? What you think is good enough for this. Good, let's move on to the second robustness check, which is parameter recovery. Now, the procedure is actually very similar here, but the goal is a bit different. We want to determine here if the parameters that we in our model are distinct and behaviorally specific. So what we do here is we take either participant parameter estimates or some prior guesses to simulate data. So we can take some parameters on the x-axis that we use to simulate data exactly the same way as before. It can even be the exact same framework as before. And now we would look at we're interested not in how well it fits or how well which model is the best fit, but for the same model, what parameter values do we then estimate back, right? So here's a plot of exactly the same alpha and beta from a softmax Q-learning model that we described earlier, but from this Wilson and Collins 10 simple rules paper, if you like. And what they're showing is that these gray dots are rather kind of outliers, but the rest of these red dots give you a relatively good fit. And this dashed line represents, I think, y equals x. So that would be a perfect fit, right? So essentially what we would like to see is that all the parameters that we estimate are well correlated on and well mapped to this kind of y equals x line from a simulated model. Okay, from a simulated parameter, sorry. In a recent preprints by one of my former master's students, Anna Giron, and collaborators Simon Soranka, we have done what we call a counterfactual parameter recovery, or kind of which is a bit more an overpowered way to do parameter recovery, where we also systematically vary parameters across a wide range of possible values. So rather than only taking the parameters we got from participants, we kind of iteratively held one parameter fixed and varied all the other ones across an entire range of values to simulate data, and we still get really good fits from parameter recovery. And here we often report it using a correlation. This is Kendall's Tau, which is a rank-based correlation method, and this gives a pretty robust measure of whether or not we're getting similar parameters back from when we do the simulation. So here we have some. I'll refer to the code notebook because we have some code where we run parameter recovery for our Q-learning agents. So we simulate data from 20 Q-learning agents with different parameter values with the same parameters as before. And then we try to estimate them using maximum likelihood estimation, which is the simplest possible approach. And we nevertheless, despite using the simplest possible approach, we still get relatively good estimates. So this is only 20 data points, so we can get much more. Alpha seems to be very well correlated. So this is a true generating alpha. We simulated them across a wide range of alphas, and we recovered highly correlated parameters back, right? So maybe this dot is not so great, but the rest is quite good. And for beta, we also get pretty good recovery. Here, the beta, we have a larger range of possible beta values, right? So linear regression is probably not the right measure here, but we're just plotting for simplicity. And overall seems to be pretty well correlated. You'll note that in the Wilson and Collins, they plot beta on log scale, right? So you might want to do a log transform as well. And these show that there's pretty good recovery for this very simple model. And I want to maybe stress that you want to do this before. It's often a good idea to do this before you collect data, because you might want to change the parameters of your experiment. Maybe you don't have enough rounds of the task. You don't have enough data points to be able to reliably estimate these parameters using your modeling approach. And this will suggest that you should change the structure of your experiment. So you might have some sets of parameters where it's very difficult to estimate parameters, and you have a high uncertainty bounds, and some areas where you get reliable estimates, right? All right, I'm going to move on now. We'll have some more discussion later. So the third kind of robustness check I want to mention was something that Stefano brought up in this really nice text paper from 2017, which is that goodness of fits don't always tell the full story, right? And he illustrates this very well with this one model here, which I think this model is making predictions about choice variability, not primarily trying to predict choices, but the model doesn't capture this aspect of human behavior that seems to be quite important, right? So as the number of the length of sequences, sequence length of your sequence increases, human choice variability increases, right? So these black dots, the gray dots represent human behavior, but this one model just is completely insensitive to this aspect, right? So in some ways, by plotting this, you can falsify this model. It might still do reasonably well in the actual log loss approach to model estimation, but it doesn't capture this essential feature of human behavior. It's rather another model that does should be preferred, right? So you can't tell the full story just using the goodness of fit measures, and you also want to essentially this is an approach to try to check that the models are reproducing important patterns of human behavior that you're interested in, right? So maybe this is a variable that you're not interested in at all, right? And so maybe there's other behavior patterns that humans produce, but your model is not trying to capture. That's also okay, right? So you don't have to capture every aspect, but if it's a crucial and important part of the story, then you want your model to also be able to reproduce that. I also want to mention we talk about value learning in our reinforcement learning models, and sometimes you also want to validate that people's value representations actually reflect what your reinforcement learning models are learning, right? We have talked about Q values, right, earlier, and how that actually corresponds to what people actually have. So one way to also do this is from the paper of mine, we actually ask participants to make value judgments about stimuli. And we find as our model that's estimated based on choice data is also able to reproduce those same patterns. For the model, the GP model here, the orange also captures participant estimates. So when participants estimate larger rewards, the model also is able to capture this, even though it's estimated on a completely different set of data based on choices. And we also want to make sure that the models can simulate performance that matches human performance as well, right? That we can, and one thing we might also want to do is that want the model to replicate differences across different experimental manipulations or from different populations. So here's a developmental study where we're capturing behavior in humans from the ages of 5 to 55. Human performance are in these gray lines with the error bars also in gray. And our GPUCD model is also able to capture patterns, differences across different age groups, and also able to capture this kind of decaying learning rates for some of these participants as well. So this is another way to get additional evidence that not only are your models fitting well, because fitting doesn't always tell the full story, but also able to capture aspects of behavior that you're interested in. Here, though, I think we actually might have assimilated more data than we had participants. We ran more simulations where we sampled from the population of parameters in order to get reliable learning curves, right? So the human curves here have the error bar. I think for the model, we simulated more data, so we have reliable means without any variability here. So in our notebook again, I also run some simulations where we don't have any real participant data, but we can simulate data using our Q-learning agents. And one thing I thought to test is that whether or not we can detect any differences in the learning curves based on either low or high beta values or low or high alpha values. And so what I just did was we had this very simple set of 20 agents, essentially that we simulated data for. And I essentially just did a median split on alpha and beta, right? So we have low alpha here, high alpha there, low beta there, high beta there, and all the combinations. And I'm showing the simulated learning curves for these agents. And one thing that you might already be able to pick out is that the low beta models don't have kind of as clear learning rates, learning curves as the high beta regime, and the high alpha has initially much steeper learning curves, but maybe they don't plateau as high as the lower alpha does, right? These are kind of slow, but they're higher. Although this is a very small set of data, just to illustrate that we should be able to capture differences in parameters from the simulations. And this is a good fan check to also run. All right, so I'm gonna conclude this tutorial with a general recipe for cognitive modeling. And this is not a fixed step-by-step instruction that we want to give you, but rather it's a set of adaptive principles because you want to be able to adapt to whatever situation that you're actually in the world. There's this great show, Iron Chef, that some of you are familiar with, where these chefs have to cook a fantastic meal in 1 hour based on some secret ingredient that's revealed to them very dramatically, being apples or squash or pumpkins. And that's essentially the situation that we find ourselves in our own research, right? There's going to be specific details and circumstances for our own tasks that are going to be dramatically revealed to us. And so we can't just follow a step-by-step instruction, but rather we have to adapt the principles. Ultimately, though, this is kind of a general recipe that should be quite robust to those different kind of the uniqueness of your own experiments and research questions. So the first step, of course, is what are your hypotheses? Generate good hypotheses and then turn them into models, right? We want to avoid the kind of vagueness of verbal theories, and by grounding them in concrete computational mechanisms in specific computational models. Next, how will you estimate the model parameters before the model comparison? Figure out which approach that we described you're most comfortable with and seems appropriate for the data. Then you want to test if that framework is robust. And as I mentioned previously, it's often a great idea to do this before you conduct the experiment, because by running this analysis, you get some more confidence that your experiment can actually differentiate between your models, that your models are going to be capturing something uniquely specifiable. And if it doesn't work out, you might want to rethink your task. You might want to rethink your models, or you might consider a more robust modeling framework that is less prone to overfitting and has a more accurate parameter estimation. Step 4 then could be the stage where you collect your data. Step 5, analyze and interpret the results. You've already done all the analyses. You had to click play essentially, right? Plugging in your participant data instead of the simulated data you've been working with. And then lastly, you still might want to test the recoverability works with the specific set of parameters that participants have. All the parameter recovery and model recovery approaches I mentioned previously, prior to the data, you're making your best guess about what parameters you get. The parameters you actually get might be quite different, and that other different regime of parameters might alter your recoverability results. So you might also want to run it again as a final check. And ultimately, I think as I already mentioned, or brought up the issue, like how do you know which approach is right? And ultimately, it's about what you can justify both to reviewers and yourself, right? This is going to be the true litmus test of how you decide what to do and which best approach to use. And I want to conclude with some social learning specific challenges. I feel like a lot of the modeling materials and framework, you start quite simple with reinforcement learning, but a lot of it is focused on individual learning, right? A lot of the materials and resources available are focused on individual learning. I want to really focus on challenges specific to social learning. So first of all, one big challenge is that, as we've shown with Rogers paradox earlier, social learning has frequency dependent fitness. The performance of both real and simulated agents don't only depend on the model parameters, but also the makeup of the group they're interacting with, right? So I talked about simulating learning curves. Well, if those learning curves are based on social learning tasks, how well you perform with your set of parameters also depends on what other people are interacting with, right? And so this means that sometimes it's difficult to simulate realistic settings because you also have to make sure that the group is also being simulated realistically. You can't just simulate an individual agent. It also means that objective performance often can't be demonstrated with a single simulation, but maybe require evolutionary simulations where we allow parameters to mutate over time, and we observe what groups emerge, what populations of parameters emerge through that. So it's harder to kind of come up with rational models in that sense. We've also only covered conformity bias social learning strategies in tutorial 2, which are the social learning strategies that treat all other individuals exactly the same. As we saw with Ariana's talk this morning, yeah, even animals like meerkats, my apologies to them, even they have selectivity in how they learn from other people, right? They're more influenced by the dominant females, and human social learning is not any different. Much of social learning, in fact, is selective in learning from successful or prestigious or higher ranked individuals. Rather, we need models to account for these selectivity biases, but in a way that avoids kind of ballooning complexity, right? So value shaping and decision biasing essentially learn from all other individuals as if they're all the same. We haven't even covered more selective social learning strategies here, where we would be paying more attention to some individuals more so than others. And lastly, we've only very briefly touched on theory of mind at the end of tutorial 2, where individuals infer the hidden mental states of others. As you probably saw from Natalia's talk, that's a really important part of human collaboration and cooperative behavior. But modeling theory of mind is very difficult, even using sample-based approximations, right? So just like Bayesian model inference, model estimation is approximated with MCMC sampling, you can also use similar sample-based approaches to model this intractable Bayesian problem of theory of mind inference. But even with sample-based approximations, it's a very difficult framework. And we also had this issue of infinite recursion, right? Which is also very difficult to model in tasks that are more realistic and less simplistic, where we have this infinite recursion of an agent reasoning about what other individuals think about themselves ad infinitum forever. So this is an additional complexity issue with theory of mind as well, because we can have this infinite recursion loop. Ultimately, capturing sophistication of social learning strategies will accomplish sort of trade-off, right? We may need to simplify individual learning mechanisms in order to better study the social learning mechanisms that we're interested in, right? We can't have everything at once. We can't have a map the size of the empire. We can't have our cake and eat it too. And so in this sense, we have to be careful about what types of hypotheses we're interested in studying, what types of mechanisms we want to focus on, and that may come at the cost of ignoring or downplaying other aspects of behavior in order to be able to estimate these phenomena reliably. I want to conclude with some recommended reading. This is far from a be-all, end-all kind of description of approaches to computational modeling. This great book by Stephen Dudgosky and Simon Farrell is fantastic. I highly recommend it. Richard McElrath has kind of really revolutionized Bayesian statistics with a very accessible and also funny and personality-filled textbook on statistics. It doesn't seem possible, but it actually is. Marco D. Lee and E.J. Vlachomakis have a very influential course on Bayesian cognitive modeling. I think that also uses JAGs, right? Maybe someone else can tell me. And then also Alberto Cherby, Alex Masudi, and Marcus Mola have this really fantastic book. I guess, is it a book down? Yeah, it's a book down. Right, essentially a code notebook for modeling a culture evolution. Highly recommended. So these are some kind of ways you can extend your understanding. And again, all the code notebooks are available online. So thank you very much. And well, I will take some time for questions now.